During the early 1940s, a great conflict raged. A critical lifeline of supplies crossed the vast, unforgiving Atlantic Ocean. Convoys of cargo vessels, essential for the Allied effort, journeyed from North America to Great Britain, carrying vital goods and equipment. However, a silent menace lurked beneath the waves. Submarines, known as U-boats, were disrupting these crucial supply lines with devastating effect. These undersea craft created a high-risk environment for the convoys, causing significant losses and jeopardizing the flow of supplies. The core of the problem was a vast stretch of ocean in the middle of the Atlantic, beyond the reach of land-based aircraft. This zone, ominously known as the Mid-Atlantic Gap, was where convoys were most exposed and without protective air cover. Aircraft of the era simply didn't have the range to patrol this gap, leaving a dangerous blind spot for Allied forces. This strategic vulnerability was a constant source of anxiety for military planners, who desperately sought a solution to protect their ships. Closing the gap was paramount, but how could they establish air power in the middle of the world's second-largest ocean? The answer seemed to lie with aircraft carriers, but building enough of them presented a whole new set of challenges. The most logical solution was to deploy aircraft carriers. These floating airfields could take air power wherever it was needed. By placing carriers within the Mid-Atlantic Gap, they could provide the crucial air cover needed to safeguard the convoys. The ideal scenario involved a large fleet of these vessels, creating a continuous protective umbrella over the supply routes. But there was a major obstacle. Building a conventional aircraft carrier required an immense amount of a very precious resource: steel. During this period of global conflict, steel was in desperately short supply. Every ton was already allocated for other priorities. The existing steel production was being channeled into manufacturing tanks, other types of ships, and essential armaments for ground forces. The dream of a massive new fleet of steel carriers was simply not feasible. The resources were just not available. The problem seemed to be a paradox. To save steel ships, they needed to build more steel ships they didn't have steel for. It was a classic catch-22. Conventional thinking had hit a wall. A new, radical idea was needed to break the stalemate. This is when an unconventional mind entered the picture, a man who believed the answer wasn't in a factory, but in nature itself. Enter Geoffrey Pyke, an English journalist, inventor, and educationalist. He was a brilliant but deeply eccentric thinker. Pyke was a true polymath, known for generating a constant stream of innovative, if sometimes wildly impractical, ideas and inventions. His mind worked differently from others, connecting seemingly unrelated concepts to devise novel solutions to complex problems. It was this reputation for outside-the-box thinking that brought him to the attention of the highest levels of the Allied command. Lord Mountbatten, the chief of combined operations, was actively seeking radical ideas and was intrigued by Pyke's record. Pyke was recruited to work at Combined Operations Headquarters, a department tasked with developing novel equipment and tactics. He was presented with the seemingly impossible Atlantic problem: create floating platforms for aircraft without using precious steel. While others were constrained by thoughts of metal and manufacturing, Pyke's mind wandered to a completely different realm. He considered the vast, frozen landscapes of the Arctic, looking for a material that was abundant, cheap, and strong. And there, in the icy wilderness, he found his inspiration, an idea so audacious it was almost unbelievable: use ice itself. Pyke's initial proposal was breathtaking in its simplicity and scale. Why not use a natural iceberg as an aircraft carrier? He envisioned leveling the top of a large, stable iceberg to create a runway, effectively creating a massive, unsinkable landing strip. The interior of the iceberg could then be hollowed out to house aircraft, crew quarters, and storage facilities. It would be a floating island of ice, immune to conventional maritime threats and built from a material that was entirely free. The idea, codenamed Project Habakkuk, was met with initial fascination. The sheer audacity of it was compelling. However, scientists and engineers quickly pointed out some critical flaws with using natural icebergs for this purpose. For one, only a small fraction of an iceberg is visible above water, making them inherently unstable and prone to rolling. As an iceberg melts or calves, its center of gravity can shift suddenly, causing it to capsize without any warning. Furthermore, natural ice is surprisingly brittle and can fracture unexpectedly, making it a poor structural material for such a vital asset. The grand idea was on the verge of collapse, but Pyke's team was about to make a discovery that would change everything. To solve the problems of natural ice, two scientists at Brooklyn Polytechnic were tasked with creating a better version. They experimented by mixing various materials into water before freezing it, hoping to add strength and durability to the ice. The breakthrough came when they tried adding a small amount of wood pulp, essentially sawdust, to the water. When frozen, this mixture of just 14% wood pulp and 86% water created a new, miraculous substance. Named Pykrete in honor of Geoffrey Pyke, this new material had incredible properties far superior to ordinary ice. The wood pulp fibers acted like rebar in concrete, creating a composite material with remarkable tensile strength. It was as strong as concrete, resistant to shattering, and could withstand immense pressure without breaking. Even more impressively, Pykrete was incredibly slow to melt. The outer layer of wood pulp insulated the ice within. It could be sawn, drilled, and machined just like wood, making it a surprisingly versatile construction material. With this super material, the project was reborn. They now had the perfect substance to build their unsinkable aircraft carrier. To get the project fully approved, Lord Mountbatten needed to convince the Allied leaders of Pykrete's amazing properties. He decided a live demonstration would be far more effective than any report or diagram. He planned a bit of showmanship. During a high-level conference, he had 2 blocks brought into the room, one of ordinary ice and one of Pykrete. To demonstrate their comparative strengths, he unexpectedly pulled out his service sidearm, stunning the assembled dignitaries. He first took aim at the block of ordinary ice and discharged the firearm. The effect was immediate and predictable. The block of ice completely shattered, exploding into countless tiny fragments that sprayed across the room. Next, he turned his attention to the unassuming block of Pykrete, aiming carefully at its center. He discharged the firearm again, but this time, instead of shattering, the Pykrete block proved its incredible strength. The projectile ricocheted off the block, zipping across the room and reportedly embedding itself in a wall near an admiral. Though chaotic, the demonstration was a resounding success. The project was immediately given the green light with enthusiastic support. With full backing, Project Habakkuk moved into the design phase. The plans that emerged were for a vessel of truly epic proportions. The proposed ship would be 2,000 feet long and 300 feet wide, making it the largest naval vessel ever conceived. To put its size into perspective, it would dwarf every other aircraft carrier of its time, being more of a floating island than a ship. Its hull, 40 feet thick and made entirely of Pykrete, would make it virtually impervious to torpedoes and other threats. Construction would require 1.7 million tons of Pykrete, which itself would need 280,000 tons of wood pulp mixed with water. It was designed to carry up to 150 twin-engine bombers, a far greater capacity than any other carrier in service. To prevent the massive structure from melting in warmer waters, a complex refrigeration plant would be built into the hull. A network of ducts carrying chilled air would run throughout the ship, keeping its temperature at a steady 3 degrees Fahrenheit. With a displacement of over 2 million tons, its slow speed was a drawback, but its sheer size made it a formidable platform. The design was complete, a testament to incredible ambition. The next step was to prove it could actually be built. To test the theories, a top-secret construction project began in a remote location, Patricia Lake in Alberta, Canada. A small prototype, measuring 60 feet long and 30 feet wide, was planned to be built on the frozen lake during the winter. The workforce consisted largely of conscientious objectors who worked in secrecy, unaware of the project's ultimate purpose. Using local materials, they harvested large blocks of ice directly from the lake and mixed them with wood pulp. A small wooden structure was built first, which would house the refrigeration machinery needed to keep the vessel frozen. A 1-horsepower refrigeration unit was installed, small but powerful enough to keep the 1,000-ton prototype solid. The entire operation was disguised as the construction of a new boathouse to maintain secrecy from the local population. The team worked through the brutally cold Canadian winter, successfully completing the scaled-down model. As spring arrived and the lake began to thaw, the prototype floated perfectly, proving the core concept was sound. The experiment was a success. It demonstrated that a large Pykrete structure could indeed be built and maintained. Despite the prototype's success, the realities of scaling up the project began to cast a long shadow over its future. The estimated costs spiraled. The massive refrigeration plant alone would be incredibly expensive and complex to build. Logistics were a nightmare. The amount of wood pulp required would cripple the paper industry, a vital part of the communication effort. Ironically, the massive refrigeration plant and its machinery would require a huge amount of steel to construct. This defeated the project's primary purpose, to build a carrier without diverting large quantities of this scarce resource. As these problems mounted, the strategic situation in the Atlantic began to change dramatically in the Allies' favor. Portugal granted the Allies landing rights in the Azores, a group of islands located strategically in the mid-Atlantic. This allowed them to establish air bases on the islands, providing a fixed, unsinkable platform for long-range patrol aircraft. Combined with new long-range bombers, the mid-Atlantic gap was effectively closed. The U-boat threat was largely neutralized. The primary justification for Project Habakkuk, the very problem it was designed to solve, had simply ceased to exist. With its purpose gone and its costs ballooning, Project Habakkuk was officially canceled in late 1943. The monumental dream of a fleet of ice aircraft carriers melted away, relegated to a fascinating footnote in history. But what became of the prototype, still floating in Patricia Lake? Its job was done, and it was simply abandoned. The refrigeration equipment was removed, and the structure was left to the elements, expected to melt in the summer heat. However, the incredible insulating properties of Pykrete meant that it melted far, far slower than anyone anticipated. The 1,000-ton block of super ice survived that first summer and the next. It took over 3 years to vanish completely. Today, the remains of this secret project still lie at the bottom of Patricia Lake, a destination for curious scuba divers. On the lake floor, they can find the collapsed wooden framework and parts of the refrigeration system, preserved in the cold water. Project Habakkuk is remembered as one of the most audacious, imaginative, and gloriously impractical military ideas ever conceived. It stands as a powerful testament to the boundless ingenuity that can arise when conventional thinking is no longer an option.